Okay. Hello, everybody. Oh, that's loud. Sorry, I won't lean in so close. Okay. So I'm happy to see so many different faces in the audience tonight. And the goal of this community lecture was to bring together many different communities from Brunswick, the mathematicians visiting from the conference, and students from Bowdoin, and math students from local schools, junior high schools and high schools, parents, teachers, and community members. So it's exactly this type of interaction which makes living in a town like Brunswick so meaningful and so much fun. So a warm welcome to all of you from the math department at Bowdoin. And now for our speaker. I've known Michael Kleber for a long, long time, and it is a great pleasure to introduce him to you tonight. Dr. Kleber received his PhD in mathematics in combinatorics from the University of California at Berkeley and held a prestigious National Science Foundation postdoctoral position at MIT. He subsequently worked at the Broad Institute of Harvard and MIT, focusing on efficient algorithms in computational biology and speech recognition, before beginning his current position at Google. Throughout this time, Michael was an active contributor to the Mathematical Intelligencer, a mathematics journal full of fun recreational mathematics. His column included articles that he wrote, such as the gold bug variations about random walks, and the best card trick, which some of you solved as homework in Math 2020 at Bowdoin. As Dr. Kleber currently works for Google, I thought an appropriate introduction to him tonight should include a Google image search for his name. After all, he works for Google. There shouldn't be anything out there that he doesn't want us to see. And so here are the results of my search. So I have known Dr. Kleber for almost 25 years, and I can tell you that he didn't make the first row of images. I have never seen any of these people in my life before. So I figured I had to do the Google search again. And I can tell you that there are people on here, like this person, who are definitely not Michael Kleber. But eventually I found him. And if you want to know more about Dr. Kleber, you can Google him yourself. So, I ask you to join in welcoming Michael Kleber, apparently an international man of mystery, a fine mathematician and programmer, a true mathematical enthusiast, and my good friend at Bowdoin College tonight.
Thank you, Jen, I think. Yeah, that's right, the one in the tube. That's my, my alter ego, yes, indeed. Okay, let's see. Where are we? Present. Good. Okay, hello, welcome. Thank you, Jen, and thank you, the entire Bowdoin and Brunswick communities for inviting me. I'm delighted to be here and to be talking to such a diverse group. The topic is pretty diverse as well. I hope it all goes well, but I guess we'll see. Okay, so I'd like to start with a math puzzle because this is what I spend my time doing, thinking about a variety of different puzzles, not professionally in my job as working for Google. I think about a lot of puzzles there too. This is not one that came up in a Google context, although I'll point at some places where where some of the tools we use to try to understand it head in the same direction as some Google stuff. Okay, so here's the puzzle. You have 1,000 bottles of wine, and one of them is poisoned, okay? And needless to say, you would like to know which the poisoned bottle of wine is so as not to accidentally imbibe. And in order to do this, you have 10 rats that you can use as taste testers. So this is a problem you're welcome to think about, but only for a few seconds, because I'm going to tell you the answer right away. There's a simple solution to this, which is binary search, right? So I take my first rat, and I have my computer-controlled wine pouring system make a glass of wine that has like 1 drop of wine from each of half of the bottles of wine. And then either that rat lives or that rat dies, and I know whether the poisoned bottle of wine was in the 500 bottles that that rat tasted from or in the other 500 bottles that it didn't taste from. And then once I've cut the set of possible wine bottles in half, I can use rat number 2 for 250 of the remaining bottles and cut it in half again, and so on. And since you take 1,000 and you cut it in half, take 1,000 and cut it in half 10 times, you're all the way down to 1 bottle. Right? In fact, we could start with 1,024 bottles of wine, and that would be just enough with 10 rats for us to find which one is poisoned. Okay, everybody got that? Good so far? Okay. So that was too easy. So I forgot to tell you, actually there's something that makes this harder. Actually, the way this poison works is when the rat tastes the poison, it doesn't die right away. The poison only takes effect after an hour. So if I did binary search, it would take me 10 hours to find out which bottle of wine was poisoned if I just did it the simple, naive way. Instead, what we need is a non-adaptive approach, by which I mean a version where you have to decide which rats drink from which bottles of wine first. And then you wait an hour, and then you find out which rats lived and died. And ideally, I would like to use all these bottles of wine for a party that I have starting in an hour. It's like 8:08, and guests are showing up at like 9:15, so I really don't have time for much more. So I only have an hour, and we need to figure out which bottle of wine is poisoned. So we can't do the simple thing, okay? So it turns out that we can still use binary search. It's great. Binary search is wonderful. You can do exactly the same thing, except that you can have all the rats do their thing at the same time. You can have rat number 1 taste half of the bottles of wine, the half on the right. And you can have rat number 2 taste half of the bottles of wine, the half that's on the bottom. And you're actually having rat 1 do what it would have done already, and rat 2 is doing both the job it would have done if rat 1 had lived and the job it would have done if rat 1 had died at the same time. And you can have rat 3 again taste half the bottles of wine, etc. And all the rats can do their tasting first, and then we can see who lives and who dies, and find out at the end. What we're essentially doing here is numbering the bottles of wine in binary, right? Every bottle of wine gets a number written in base 2, which is 10 bits long. That lets you count from 0 to 1,023, right? And so bottle 152, when you write it out in binary, has 3 ones in binary in the 3rd, 6th, and 7th bits. And we say, okay, rat number 3 is going to taste everything whose 3rd bit is a 1. Rat number 6 tastes everything whose 7th bit is a 1. Rat 7 tastes everything whose 7th bit is a 1. And now we can wait an hour, see which rats die, and we can know, based on that, which is the poisoned bottle of wine. Right? And as a matter of fact, since living rats are kind of short and squat and rolly and kind of like zeros, and the dead rats, if you hold them up by their tail, are tall and skinny and kind of like 1, so it just kind of reads out by looking at the rats which ones are alive and which ones are dead, and it just says right there in binary the identity of the poisoned bottle. Okay, great. Everybody with me still? Great. Okay, so that was too easy. That's not actually the problem that I want to solve tonight. Actually, the problem I want to solve is 2 of the bottles are poisoned. So that's a lot harder, it turns out. We're suddenly in the realm of something called combinatorial group testing. In combinatorial group testing, you have n items, in this case 1,000 bottles of wine, and d of them are defective. In this case, 2 of them are defective. And the kind of tests you're allowed to do are there any defective items in this particular subset, right? So that's you take a bunch of rats and you give them some wine from some subset of the bottles, and you find out if any of those bottles are bad. And combinatorial group testing turns out to be a pretty important topic. Like, there's a whole book on it called Combinatorial Group Testing and its Applications. I am not going to give a survey of this topic because it is a much larger topic than I can possibly talk about this evening, and I actually don't know a lot about it anyway, so I'm just going to pick and choose the things to talk about. But it turns out that there are a lot of applications of combinatorial group testing. So the sorts of things that I've run into at some point in my career, as Jen mentioned, I did biology for a while, and this sort of thing turns out to be useful in biology. If you have a large number of specimens and you want to find out whether there is if you want to screen for DNA or screen for carriers for something, you can pool a blood sample from a large number of individuals and then use a DNA probe to test if any of the individuals had this piece of DNA that you're looking for. One of the algorithms that's used for TDMA access for sharing channels among different radio communications devices is based on combinatorial group testing. There's an information retrieval application that's based on combinatorial group testing and finding which documents are relevant to a particular query. So there are a bunch of things that use this. As a matter of fact, the first mention of this problem was a paper by Dorfman in 1943 in which the actual problem that he was trying to solve was during the draft for World War II, where there were tens of thousands of recruits and they needed to test everybody for syphilis. And instead of using one syphilis test for each individual, they wanted to cut down the number of tests, and they could do it by taking the serum and pooling them from lots and lots of enlistees and finding out if any of them were tested positive for syphilis. Right? So in case you thought the wine and the rats in wine bottles thing was like the least appealing possible version of this problem, it turns out I'm really doing pretty well compared to something that's more historically accurate. Okay, so we've got 2 poison bottles out of 1,000, and as before, it takes an hour for us to find out whether rats lived or died, and the question is, what can we learn an hour from now, right? How many rats does it take to find the 2 poison bottles? Well, since I used binary for doing this the first time, here's a way that one could possibly do this. You could try, let's label the bottles in base 3 instead of in base 2 and see what happens. So this is a pretty good way, like the best way I know to actually use rats to figure out which the poison bottles are. And bear with me for a minute because it takes a little thinking about to understand exactly how this works. So there's a bunch of rats that we're going to use, and each rat has a job that indicates which bottles of wine it's going to be tasting. It's not as simple as it was in binary, where there was a rat that tasted everything with a 1 in the ith bit or something like that. So we do want to do something like that. So there is a rat that drinks, let's say, all bottles whose 5th digit is a 1, right? So we're going to write the numbers on the bottles in base 3, and they're going to be like 7 digits long, right? Because 3 to the 7th is large enough to be more than 1,000. So we're going to have a bottle that we're going to have a rat that tastes like every bottle whose whichever digit has whichever value. That's going to take us 21 different rats to do, of course. And then we need some more rats. That's not enough for us to figure out which the poison bottles are. We're going to have another rats that do something like, there's a rat that drinks all bottles whose 2nd digit and 4th digit are the same as each other, right? The digit 2 equals digit 4 rat. And so those rats are going to be drinking like, so each rat is going to taste like 1/3 of the wine bottles in this scheme, roughly, right? Okay. And let's think through how to decode this, right? So what can you learn from the first kind of rat? The kind of rat that tastes each wine bottle based on just looking at one of its digits? Well, if we look at the 3 rats who taste like based on the 1st digit of the serial number of the wine bottle, then like if the 0 in the 1st digit rat died and the 1 in the 1st digit rat died and the 2 in the 1st digit rat survived, of course, one of the 3 of those has to survive, then we know that the 1st digit is either a 0 or a 1. Whereas in this case, we know that the last digit has to be a 2 because only one of those 3 rats died, right? Everybody clear? So we know that both bottles that are poisoned end with a 2. One of them starts with a 0. One of them starts with a 1. Okay, but that's not enough. So I put a little description here where the 1st and the 3rd and the 6th digits are still ambiguous after doing this because there are 2 different rats that died. That means it's not enough for us to identify exactly which 2 bottles are the 2 that are poisoned, right? Based on this information that you have so far, there's like 8 different bottles that could be poisoned because you have to go with each combination of the value for the 1st, 3rd, and 6th digit, right? Okay, but now we can use the other kind of rat to help us figure out which it is. Remember, there was a rat that tasted every bottle whose 1st digit and 3rd digit matched. If that rat died, that means that there's a poison bottle that has the same number in the 1st digit as in the 3rd digit. And since there's a 1 in the 1st digit and a 1 in the 3rd digit, we can figure out that those have to be the same bottle of wine. So there's a poison bottle of wine that starts with a 1 in the 1st place and a 1 in the 3rd place. And likewise, this green rat over here who tasted everything whose 3rd digit and 6th digit matched, that one lived, which means that we can tell that there is not a poison bottle that has a 2 in the 3rd place and a 2 in the 6th place, so we know that those bits values cross over with each other. So if you think about it just a little, you can convince yourself that this is actually enough for us to figure out which are the 2 poison bottles. In fact, there's a lot of redundant information here. Because of transitivity, it turns out that you can figure out something about which rats had to die. You have more than enough information to do it. Okay, so if we have so many bottles, if we have like 3 to the t bottles, so that t is like the length of the serial number on the bottle in ternary, then that's going to take a bunch of rats. It's going to take like 3T rats that taste based on one digit, and T choose 2 rats that taste based on 2 digits being equal to each other. So for 33 rats, you would be able to do this for up to 729 or 3 to the 6th power bottles. And to actually get up to above 1,000, you're going to need 42 rats, right? That's an awful lot of rats. Okay. So let me just introduce a bit of terminology here. This will be useful later on, but since we have this nice concrete example in our hands, let me talk about what we're building here. What we just built is called a binary superimposed code, right? So if you made a matrix, a giant 1,000 by 42 matrix, and you put zeros and ones in this matrix, where the 42 rows of the matrix correspond to the 42 rats, and the 1,000 columns of this matrix correspond to the 1,000 different bottles of wine, right? Now you have this giant matrix, and the columns of this matrix are each 42-bit long vectors, right? With zeros meaning this rat didn't taste this wine, and ones meaning this rat did taste this wine. And mathematicians have found uses for these kind of matrices before. The amazing thing about this matrix is its columns are called a binary superimposed code. That's a bunch of bit strings where if you take any column and any other column and OR them together, like add those two things together, except that 1 + 1 = 1, right? So you OR them together and you know which bits were ones in either of those two columns of the matrix, you can figure out which two columns they were, right? If you're used to thinking about codes and have thought about coding theory before, you're probably used to error correcting codes, right? Where if somebody gives you a code word and one of the bits in the code word is wrong, like it's flipped, for example, then you can reconstruct what the original code word was and what bit was changed, right? So the code words have some redundancy built into them. So the code words that are the columns of this matrix have a different kind of redundancy. Somebody could send you a message that had 2 code words at a time squashed on top of each other, and you could pull them apart and still see which the 2 different code words were that were sent to you. Okay? Okay, so the question is, can we do better than this binary superimposed code that lets us label 1,000 bottles or up to 2187 bottles with 42 rats? And the answer is maybe we can do better, I'm not sure, but we can't do a lot better. We can't do enough better. And the reason we can't is because of an information theoretical argument, which I will give you now. If you think about it, if I have 1,000 bottles and 2 of those bottles are poisoned, then there are a lot of possibilities for which pair is the pair of poisoned wine bottles. In particular, there's 1,000 choose 2 different pairs of bottles, right? Not quite 1,000 squared because it's 2 different bottles, and if you reverse the order of the bottles, it's the same. So there's 1,000 choose 2 different pairs of bottles. And with 18, if I had 18 rats, if I only had 18 rats available to me, then some of those rats are going to live and some of those rats are going to die, and there's only 2 to the 18th different things that can possibly happen, right? If I let my rat, no matter what way I use of assigning rats to wine bottles, there's only 2 to the 18th different events that I might observe when I wait an hour and see who lives and who dies. And that is only like 262,000 different possibilities. And since there's 500,000 different possibilities that I have to distinguish between, there's no way that looking at what happens to 18 rats can possibly give me enough information to do it. So we need at least 19 rats to make this possible. So we know that the number of rats we need is at least 19. 42 rats is good enough. That's great, except that I only have 10 rats. So I'm out of luck. There's no way I can possibly solve this problem. Okay? So being mathematicians, now we say, oh, well, there's no way to solve that problem. Great, time to look at a new problem, time to redefine what the problem is. So now I'm going to tell you what the new goal is, the goal that I actually am going to spend the rest of the time talking about, which is not find the 2 poison bottles with 10 rats, we know you can't, but rather we want to throw away the poisoned bottles. We want to be sure we've gotten rid of the poisoned bottles and as few other bottles as possible in the worst case. Right? So I want to throw away the smallest number of bottles that we can throw away and end up with only bottles that I'm sure are non-poisoned at the end. And I think it's probably right around this point that I switch from doing math to doing applied math. I mean, loosely, a little bit applied. Okay. Okay, so let me go back to that lower bound argument that I just made. Actually, it has something new to tell us now. We have to think about this one again. The information theoretic lower bound still says there are almost 500,000 different pairs of bottles as before, and with 10 rats, there are at most 1,024 different things that could possibly happen, right? So by the pigeonhole principle, that means that there's got to be some event that corresponds to, that would cause me to throw out at least 488 different pairs of bottles, right? Because if you take how many pairs of bottles there are and you divide by 1,024, then you get, and round up, you get 488. So if every possible event has me throw out some number of bottles, there's no way I could get under 488 bottles in response to some event happening, right? If they were like kind of perfectly, maximally, equally spread out. 488 is somewhere between 31 choose 2 and 32 choose 2. So what that means is even if I packed in those pairs of bottles as ideally as possible, then I would have to throw away at least 32 bottles in order to throw away 488 pairs of bottles, right? If I only throw 31 bottles away, then there's only 465 different pairs that I can make out of those 31 bottles, and that's not enough. So the information theoretic argument on a lower bound says that I need to throw away at least 32 bottles in the worst case. There's no way I can avoid it. And actually, this is a pretty bad lower bound. I want to point this out. I don't actually have a better lower bound that I can tell you, but I can tell you that this one's pretty rotten. The thing I just said about if I throw away 32 pairs of bottles, then I could be throwing away 32 bottles. I could be throwing away 488 different pairs of bottles. That's really, really crummy, actually, as lower bounds go. Let me just to point out how grossly inefficient I'm being here. What I'm basically saying from the graph theoretic point of view is if you take like the 1,000 choose 2 edges of a k-1000, right? So you take the complete graph on 1,000 points, every point's connected to every other point, and now you get to color those 1,000 choose 2 edges with 1,024 different colors, right? So every edge is colored with a color that corresponds to the set of rats that die if the bottle on its left edge and the bottle on its right edge are poisoned, right? So each of those lines represents a possible situation we're in. Each of the colors of those lines represents which set of rats might die. And what I'm saying is, if you color this k-1000 with 1,024 colors, then each color of edge has to touch at least 32 different endpoints, right? And that's because I'm saying there's got to be at least 32 edges, and there have to be at least 488 different edges that are the same color, and if I pack those all in as tightly as possible, I could take like 32 points and have all the edges that go between them be the same color, and then that is enough to throw, that's enough that I've managed to use one color to color 1/1024th of all the edges in this graph. And that's really ridiculous, right? I mean, saying that I'm going to manage to pack in all of these edges of the same color would be really hard. You need like 32 points and like all the edges between them are all the same color. And thinking about trying to do that like 1,000 times all on top of each other on the same graph is completely ridiculous. So actually, I'm sure that you can actually make this lower bound substantially better. And please go ahead and figure it out and let me know. I have no doubt that this can be improved on. Okay. But now, okay, so we certainly need at least 32 rats. How many rats do we know that we can use, right? How many rats is it? Or sorry, no, we only have 10 rats. We know that we need to throw away at least 32 bottles of wine. How many bottles of wine do we know we can successfully throw away? Okay, here's a scheme to do it. We certainly can get away with throwing away only 200 bottles of wine, right? That's just you have each rat taste 1/10 of the bottles of wine, and then 2 of the rats are going to die, probably. I mean, maybe you'll get lucky and only one rat will die, but probably 2 of the rats will die. And then we throw away the wine that was tasted by those 2 rats, and we've thrown away 200 bottles of wine and the 800 bottles of wine left over, and we're good, right? Everybody happy with that so far? Everybody got 200? Okay, great. So how much better can we do? Actually, here's a little improvement on that I want to point out. Instead of having each rat taste 100 bottles of wine, we can have each rat taste 91 bottles of wine by taking 9 bottles away from each rat. And the 90 remaining bottles don't need to get thrown away when 2 rats die, because we know that each rat has found one of the 2 poison bottles, and the other 90 bottles that didn't get tasted are fine. If only 1 rat dies, then we have to throw away the wine tasted by that rat and the 90 bottles that weren't tasted by anybody, because maybe the poison bottle was in that one, we're not sure, right? But still, in that case, we end up throwing away at most twice 91 bottles of wine, right? So that's 182 bottles. Improves a little bit on the 200 bottle solution. Okay, so we're down to 182 bottles of wine, worst case. Here's another thing that we could do. We're going to keep edging this down over time. Here's another thing that we could try. Let's label each bottle, give it a serial number, just like we did before, except this time we're going to give it a serial number in base 10, so the bottles are labeled from 000 through 999. And now rat number 1 is going to taste all the bottles that have a 1 in their serial number any place. Right? I can't afford a rat to taste all the bottles whose first digit is 1. That would take like 30 rats, and I only got 10. But I can have one rat that tastes all the bottles that have a 1 anywhere in their serial number. Right? So bottle 125 is tasted by rats number 1, 2, and 5. Right? So in that case, it turns out that the worst case scenario is when 6 rats die. Right? If rats 1 through 6 all die, then which bottles of wine do I have to throw away? Well, I have to throw away all the bottles of wine that have a serial number that has 3 different digits that are drawn from 1, 2, 3, 4, 5, and 6, right? So there are 6 possibilities for its first digit, 5 for its second digit, and 4 for its third digit. So that leaves me with 120 different bottles of wine that I would have to throw away to cover all the bottles of wine that might have caused rats 1, 2, 3, 4, 5, and 6 to all die. That argument makes sense? We got down to 120 bottles of wine. We good? Okay, getting better. We're down to 120. Nice. Let's keep going. Here's another thing that I could do that is like labeling bottles with serial numbers, but now the bottles are going to be a little different. They're again going to have a 3-digit serial number, but now in the first digit, I'm just going to use the labels 1, 2, 3, and like dash, a blank. That blank is going to correspond to no rat tastes it, just like those 90 bottles that I left off in the 200 solution. Right? So the first digit of the serial number is 1, 2, 3, or blank. The second digit of the serial number is 4, 5, 6, or blank. And the third digit of the serial number is 7, 8, 9, 0, or blank. And now there's only like 4 possibilities for 2 of the digits and 5 possibilities. So there's only 80 different labels at this point. Right? So each label is going to have to get used a bunch of times. Right? Pigeonhole principle says I'm going to need like each label gets used 12 and a half times. So there's going to be 12 or 13 bottles with each label. And like all the 12 or 13 bottles that are labeled like 2-8, they get tasted by rat 2 and by rat 8, and there's no rat at all that tastes them based on their dash being in the middle digit, right? And the worst case that happens is you have to discard 8 labels, right? There's at most 2 dead rats that correspond to, there's 1 or 2 dead rats corresponding, well, 0 or 1 or 2 dead rats corresponding to the first digit in a label, 0, 1, or 2 corresponding to the second digit, and 0, 1, or 2 corresponding to the third digit. And that gets me down to throwing away 2 times 2 times 2, or 8 bottles. That corresponds to throwing away only 8 labels, right? And since there were 12 or 13 bottles with each label on them, that's at most 104 bottles. Maybe if you jiggle it around to make the rounding work out, you can be careful and manage to get down to only 102 bottles. Okay? So we're doing pretty well here. We're down to 104, maybe a little less bottles of wine that we have to go through. Okay, all clear? Here's another solution that I like. This comes from a colleague of mine, Thomas Colthurst, who's also a former mathematician, now gainfully employed at Google. Here is the most symmetric possible solution. Thomas is a big fan of symmetry, as am I, and so we have the most symmetric possible way of assigning rats to wine bottles that we could possibly think of. In the fully symmetric solution, we say, okay, the 200 bottle solution that we talked about way at the beginning, it said each rat is going to taste 100 bottles of wine, right? That's good. That's nice and symmetric. In Thomas's solution, we also have each rat taste some number of bottles of wine. It's going to turn out to be 13. There's going to be 13 bottles of wine that get tasted by each rat individually and by no other rat. And then the other thing, we're also going to have each pair of rats cooperate to taste a bottle of wine, right? And in fact, there's going to be 5 bottles of wine tasted by each pair of rats, right? So there's 13 bottles of wine that are tasted just by rat 7. There's 5 bottles of wine that are tasted by rats 7 and 9 and nobody else. And also each triple of rats is going to taste 5 bottles of wine, right? So there's 5 bottles of wine tasted by rats 1, 4, and 3, 1, 4, and 9, whatever. And that's actually not quite enough to taste all the bottles. It turns out that that leaves us with 45 bottles that are not tasted by any rat at all. And as we know, that's also a useful thing to do sometimes. We've seen some examples already. And the worst case here turns out to be what happens when exactly 3 rats die, right? And if 3 rats die, then, well, it takes a little thinking here to figure out how much wine we need to throw away when 3 rats die. when 3 rats die, it might be that the wine that was poisoned is it might be that there's a bottle that was poisoned that was tasted by all 3 of those rats, right? So there's 5 bottles like that we have to throw away. It might be that there's a poison bottle that was tasted by only 2 of those rats and another poison bottle that was tasted by 1 of them, right? So we need to throw away, well, there's 3 different choices for which pair of rats. So there's 3 times 5 bottles tasted by a pair of rats that we need to throw away. And there's 3 choices for which 1 rat would be the other one to go with them. And there's 13 bottles tasted by each of those 1 rats. So if you add up all the bottles that you need to throw away, you end up with 3 13s and 3 5s and a 5 and a 45. And altogether, that's also 104 bottles that you need to throw away. This is a nice symmetric solution. We're going to come back to this one a few times. Is this one clear? Any questions about this this very symmetric solution? Right? We're giving wine to each rat, some other wine to each pair, some other wine to each 3, some wine to no rats at all. I like this one a lot for reasons that you'll see soon. Okay, so let me tell you about binary superimposed codes. I mentioned binary superimposed codes before. You remember those were the columns of that matrix when I talked about the 1000 by 42 matrix based on the assigned using rats in ternary to taste things. A binary superimposed code, so that means a bunch of code words, a bunch of bit strings, right? A bunch of strings of 0s and 1s, where if I give you any 2 of those strings ORed together, you can figure out which 2 strings it was that I gave you, right? So there's a 10-bit binary superimposed code with 22 different words in it. I listed 11 of them on this slide here on the right-hand side if you want to quickly check to make sure I'm not lying to you. And also the other 11 are what you get by switching the first half and the last half of each of these words. You kind of swap the order of the 2 halves of the upper 5 and the lower 5 bits. So there's a 22-bit 22-word binary superimposed code of length 10. So I could use that to figure out what rats to taste which bottles, right? If I divide the wine into 22 different chunks of wine that are all the same size, right? And each of these is labeled by one of these 22 different code words, and those code words say which rat tastes which wine, and then the dead rats are either going to correspond to one of these code words, if both poison bottles were in one lot, or it's going to correspond to 2 different code words from the 2 different lots of poison bottles ORed together, because all the rats that tasted from this poison lot or that poison lot are going to die, right? So we're going to get exactly 2 words ORed together. And now binary superimposed code means I can tell exactly which 2 of those 22 lots of wine are bad, and I have to discard 2 20-seconds of the wine, which, with rounding, means only 92 out of 1,000 bottles need to be discarded. Okay? So these are a variety of ideas from different versions of coding theory that gets us down to 92 out of 100 bottles. Actually, we can do a little bit better. Let me introduce something that probably has a real name, but I couldn't figure out what it was, and so I called them k-ambiguous superimposed code. A binary superimposed code means when you OR 2 of the words together, and if I tell you 2 of the words ORed together, then you can figure out which pair of words it was, exactly which 2 words I ORed together. A k-ambiguous superimposed code is a bunch of code words, and if I give you 2 of them ORed together, maybe you can't tell exactly which 2 it was, but you can tell that there weren't, you can tell that there were like only k possible words that were the ones that were ORed together to get this, right? So if k is 2, it's back to being a binary superimposed code. With k being higher than 2, there's a little more ambiguity, but not too much. If I give you a word, you can mostly tell more or less or close to which code words were involved. That's also useful for these rats. As a matter of fact, if there were only 7, if we had like 7 bits, so if we were trying to do this problem with only 7 rats instead of only 10 rats, the largest binary superimposed code has 10 code words in it. But there is a 4-ambiguous superimposed code that I found by playing around with a little computer search that has 21 code words in it, and that means that we could use that one to throw away only 4/21ths of the wine instead of the 2/10ths that we could throw away using a regular old binary superimposed code. So that beats it a little bit. So these ambiguous superimposed codes are a little bit better, right? For 10 rats, I managed to find a 4-ambiguous superimposed code with 50 words in it that has a lot of symmetry and that I tried to draw a picture of using these decagons here that show you like where the ones are. So there's 1, 2, 3, 4, 5, 6 code words on the board there, and then there's another like 4 group symmetry operations, and you can take those 6 code words and do any of those symmetry operations to them to get more code words. So that turns out to give you 50 code words total, right? And here's sort of a picture of them. And that's pretty good. That actually lets us throw away 4/50ths of the wine bottles, which means we only have to throw away 80 bottles out of 1,000. No rounding required, because 50 goes into 1,000 nicely. Okay, so now we're down to 80 using these k-ambiguous superimposed codes. That's pretty good. So that's sort of a coding theory approach. But coding theory is not actually quite the right thing to use here, right? In coding theory, you have a bunch of different code words which correspond to bunches of bottles of wine. But as we already saw, how do we say this? If you have 10 rats, then each bottle is going to have one of 1,024 possible labels on it, right? There's only 1,024 possibilities for which set of rats tastes each bottle of wine. So you might as well really think about it as you're going to put one of these 1,024 labels on each bottle of wine, right? And the label just corresponds to exactly which set of rats taste it. And in the superimposed codes case, what you're really saying is which of the labels are labels that are good to use, right? If I use these 50 labels, and I put each one on the same number of bottles of wine, then I will end up having to throw away 4 labels worth of wine, which is going to come out to 80 labels, because each label's on 20 bottles. But actually, it doesn't make sense to talk, when you talk about the superimposed code case, you're really saying which labels are okay to use, and it makes more sense to ask how much wine should have each label on it instead. That's actually the question that we were asking with the fully symmetric solution before. Right? In the worst case, 104 rats die, so it's not the best solution that we've talked about, but it is more general than the coding theory way of looking at things, because we know that the labels that only have 1 bit in them, those are labels to put on a larger number of bottles of wine, and the labels that have more bits in them, you want to put on a smaller number of bottles of wine, right? That's because in the case where 6 rats die, for example, you know that there was no 1-bit labels that were a poison bottle of wine, because there's not enough, if one of the poison bottles of wine had only 1 bit in its label, then you would need 5 bits in the label of the other bottle to get all the way up to 6 different rats dying, right? You end up condensing things nicely by having different numbers of bits correspond to different sizes of how much wine they taste. So in general, the sort of more general version of the problem, better than the coding theory way of thinking about things, is you have 1,024 variables, which I guess will give the names x sub a string of 10 zeros all the way up to x sub a string of 10 ones. You can think of the subscript as a number written in binary if you'd like. So they're x0 through x1023, right? And each of those variables, the variable x sub, I guess I could call it x sub I, but let me instead call it x sub s, where s is a set of rats, right? And that set of rats corresponds to a bunch of zeros and ones for which rats are going to taste a certain bottle of wine, right? So you have 1,024 variables indexed by all the possible sets of 10 rats, right? And each of those variables is going to be a number between 0 and 1. And it's going to indicate what fraction of the wine is tasted by exactly that set of rats, right? So these variables all have to add up to 1. The variable x sub 00000 is how much wine is tasted by none of the rats, right? The variable x sub 111 is how much wine is tasted by all of the rats, which is probably none of it, because it seems like it's probably a pretty bad idea to have any rat taste from all the bottles, right? I mean, yeah. Or any bottle tasted by all the rats, rather. Yeah, because, I mean, yeah, anyway. So these are gonna all add up to 1. And how do we know in this version of the world when we have to throw away a bottle of wine? We have to throw away wine with label S and with label T, where S and T are 2 different subsets of the rats, if the dead rats are the union of S and T, right? The rats that died are the union of S and T, and rat set S and rat set T both were involved in wine tasting, right? If either rat set S or rat set T tasted 0 wine, then we don't have to throw away the other one, the wine tasted by the other one, even if S union T dies, right? Because there's no way it could have been an S bottle and a T bottle that were the 2 poison bottles. Okay? Okay. It turns out that this is the best thing that you can possibly do with 6 rats. With 6 rats, the best you can do using binary superimposed codes, according to like a little computer program I wrote to check it out, discards 1/4 of the bottles of wine, whereas there is an unequal weight code in which the all zeros vector goes to 7/49ths of the wine, and there's some 1 rat sets that are 1/49th and some 2 rat sets, but not all of them, that are they get 3/49ths of the wine attached to them. And the result is I can discard only 12/49ths of the wine using only 7 rats, and that beats 1/4. So these unequal weight things are valuable. They do better than you can do just using coding theory, right? Just a little bit better. I know, it's true. Like 12/48ths would be a tie, and 12/49ths is like I save a little bit of extra wine, but every drop counts. You gotta, yeah. I hope the rats appreciate this effort. Okay, so this rat just perked its ear up because I just said in the 6 rat case that 12/49ths was optimal. Optimal. That means that's the best you can possibly do. Like in the 6 rat case, I just told you the ultimate answer to this question of how much wine is it possible to save, right? If you only have 6 rats, the answer is you can save 12/49ths and that's it. So how on earth could I possibly know that? Okay. Well, I came up with that answer using something called linear programming, which is a different technique that we've not talked about today. So let me talk a little bit about what linear programming is. Just very quick introduction. For linear programming, people draw pictures like this. First, they draw a set of coordinate axes, and then they draw some lines on them because you have a bunch of linear constraints, which are drawn by lines. And then actually, those lines are all inequalities. And so one side of each line is called the good side, and the other side is the bad side. And the region that is on the good side of every one of these lines is called the feasible region, and that's what I've colored in here in yellow. And then in linear programming, after you define the feasible region, you say, I want to go as far as possible in a certain direction. That dotted arrow tells you what direction you want to go as far as possible in. And linear programming is the problem of what is the point in the feasible region that is as far as possible in that direction, and it's that point there, little red one. Okay? That's linear programming in a nutshell. Okay? Show of hands, who's seen linear programming before? How alien is this concept? Okay, great. So for linear programming, I can solve exactly this kind of problem. Linear programming is the perfect tool for the kind of problem that I just said, right? If we had the completely symmetric solution that we were talking about before, and we said, okay, there's some fraction, F1 of the wine that's tasted by all sets of rats of size 1. So each of the 10 individual rats is going to taste F1 worth of wine just themselves and nobody else. And every 2 rat subset is going to taste F2 fraction of the wine. And every 3 rat subset is going to taste F3 fraction of the wine. And then all the wine that wasn't tasted by any one of those is F0. That's the wine that's tasted by no rats at all. Right? And now I want to figure out what values to use for these F0, F1, and F2, and F3 that lets us keep the most wine. That's to throw away the least wine in the worst case. That is a perfect linear programming problem, right? It fits exactly the picture that I just showed. There is a bunch of variables, F1, F2, F3, and F0, and for each number of rats that dies, I can figure out how much wine I would need to throw away as a function of those 3 variables. Or 4 variables, I guess, but F0 is kind of, you can redefine it in terms of the other ones, so you can sort of think about it as a 3-dimensional problem instead of a 4-dimensional problem if it makes you happy. So like, for example, if 4 rats die, then what wine do I have to throw away? Well, I have to figure out what possibilities there are for how 4 rats could possibly die. Maybe it's the poison bottles are tasted by 3 rats, some wine, and some tasted by 1 rat wine, or maybe it's some tasted by 2 rats wine and some other tasted by 2 rats wine. It can't be any of the tasted by 0 rats wine because there's no tasted by 4 rats wine to make up for it, so we know that that stuff is all safe, etc. And if you look at these numbers and are familiar with Pascal's triangle, you might recognize that there's some binomial coefficients going on here, so I'll let you mull that over if you want. But anyway, what we have to do is write down this set of 6 or 7 linear inequalities, and D, the amount of wine that we have to discard in the worst case, is a variable, and I can say it is greater than or equal to, it is at least as large as what I have to throw away in each of the possible cases. And now I just need to do a linear programming thing, which is minimize D, minimize the amount I want to discard. And it turns out that linear programming is something that computers are really good at solving. Actually, it's a little weird. If you've learned about computational complexity theory, it's not like there's an easy polynomial time algorithm that does things, but the obvious algorithms for how to do it have higher computational complexity than you'd like, but in practice, they turn out to work out really well. There are some algorithms that are known to be polynomial time for how to do this that turn out to be really inefficient, and nobody actually uses them. Everybody uses the like exponential time algorithms that turn out to be really good in practice, except in some very weird, unusual cases. That's a different talk. I'm not going to go into that now. Anyway. So I can solve this, and it turns out that the answer is I can figure out fractions, f1, f2, f3, and f0 as a result. The best fractions for this turn out to, oh, I didn't write down what they were. It turns out that the best possible fractions for this are, or I don't remember what. I thought I had it written down in my notes somewhere, but I forgot to, oh well, too bad. So you can, oh, it's right there on the slide. There we go. It's 5 397ths of the wine goes to each like 1 rat subset, and 2 397ths goes to each 2 rat and each 3 rat subset, and the remaining, I don't know, I think it's 17 397ths or something like that is the stuff that gets not tasted. And as a result of all of these, actually in every one of those 6, 5, 4, and 3 line cases, the same amount of wine is discarded, and D takes on it. Those turn out to be equalities. 4 of those turn out to be equalities all at the same time. That's just like what we saw in this picture. The optimal vertex, the corner of this thing, tends to satisfy a bunch of different constraints all at the same time because it's a corner of this thing. So a bunch of these inequalities turn out to actually be equalities. And also the answer is going to turn out to always have rational numbers because it's right on the intersections of a bunch of things that are lines. And so of course, you get rational numbers as solutions. So we end up throwing away 40 397ths of this in this fully symmetric solution. So that's like a little more than 100, not percent, per mil. Does everybody know the per mil sign? It's kind of like a percent sign, but with an extra little 0 on the bottom. That's the per mil sign. You don't get to use it very often, but there's 1,000 bottles of wine, so we get lucky. So you get to throw away just a little more than 100 per mil of these bottles of wine. So it's not like the best that we know how to do. We know how to get that number down to 80, but it's an example of linear programming and lets you find a nice optimal solution for something. So for linear programming, people draw pictures like this. The thing I actually use to do a better job of throwing away wine than in anything involving coding theory is instead mixed integer programming. Mixed integer programming is a much less commonly discussed topic for undergrad classes and turns out to be much more useful for certain problems in the real world. So mixed integer programming, people tend to draw pictures like this one instead. It's just like linear programming, except that in addition to all of these inequalities that you need to satisfy, and so this feasible region you get based on these inequalities, you also have the constraints that some of the values, the sum of the variables that you're trying to solve for have to take on integer values. And so the set of points that you want to find a point that is as far as possible in some direction, just like with the linear programming case, except that the point also has to be an integer point. And if you look at this lattice of points here, this turns out to sometimes be much, much harder. This turns out to be linear programming. I can make a really big linear programming problem with like thousands of variables in it, hand it to a linear programming solver, and it can say, yeah, sure, here's the rational number, that's the answer. I give it to you. For mixed integer programming, I can write down a really big mixed integer program and say, okay, no problem, give it to a mixed integer program solver, and it'll say, yeah, okay, I'll think about that for a while, and then it'll think, and it'll think, and it'll think, and it'll think, and it'll think. And sometimes it'll tell you the answer, and sometimes it'll just die a horrible, painful death. So, the great secret here, the great surprise here, is that it's actually possible to write down this entire optimal rats wine drinking problem as a large mixed integer program. This was pointed out to me by a colleague, Veit Elser, who's a physicist at Cornell, who showed the following way of writing it in terms of mixed integer programming. So S is a subset of the rats, just like before. X sub S is, just like before, the fraction of the wine that was drunk by the rat subset S. The s's all have to add up to 1. Each s is a number between 0 and 1 because it's a fraction of the wine drunk by them. And now we introduce the integer variables into the world, right? And the integer variables are, for each rat subset S, we're going to introduce a Boolean variable, that is something that is an integer and that is constrained to be between 0 and 1. In other words, it's like a Boolean, right? It's true or false, basically. And it's equal to 1 if that set of wine got tasted by any rats. And it's allowed to be equal to 0 if no rats at all tasted that particular set of wine, right? As you saw before, the question of which wine we need to throw out very sensitively cares about which sets of wine were tasted. Right? No, there we go. And now we need a bunch of new variables and a bunch of new inequalities to encode the logic of which wine you have to throw away. So here's how it works. For every S and T and U that are 3 subsets of the rats, right? If the union of S and T is U, so if S and T are 2 sets of rats, and U is the rats that would die if S and T rats if the S wine and the T wine were both had a poison bottle in them, then we have this new variable called Z sub SU, which is how much wine we would have to throw away if that were to happen. Right? So we need to write down something which says Z sub SU is the amount of wine that you have to throw away that was tasted by rats S if rats U died. So that's a complex logical statement, and yet surprisingly you can encode it in a single inequality, right? This one linear inequality down at the bottom of the screen here. Remember, y's are variables that are Booleans. They're either 0 or 1. Right? The y's are 0 if that set of wine was not tasted, and the y's are 1 if that set of wine was tasted. So if set S was tasted, then ys is 1. And if set T was tasted, then yt is 1, which means the right-hand side is 2 minus 1 minus 1 is 0. And I'm actually saying that xs is less than or equal to z sub su. That is, z has to be at least as large as the corresponding x. But if either of those variables are 0, right, if ys is 0 or yt is 0, then this inequality disappears. This inequality turns out not to mean anything at all, because really I'm saying, okay, there's this x variable and this z variable, and the difference between them is less than 1. But these were both variables that were between 0 and 1 in the first place, right? I'm not saying anything at all if I'm saying the difference between these variables is less than 1, right? So somehow, using these zeros and ones as logical things, I managed to encode this logical relationship between what got tasted and what needs to get thrown away in a linear inequality. Okay? And now finally, f is the amount of wine that you have to throw away in the worst case. It's a real valued variable between 0 and 1. It is at least as large as what you have to throw away for each particular set U of rats that might die, right? Because that's the worst case scenario thing. If U is the set of rats that die, then you add up all the ZSUs, which are how much S-tasted wine has to be thrown away if rat set U is the one that dies, and we end up with this bunch of linear equations that tell you how much wine to throw away. And now we just have to find the x's that minimize f. Okay, so as I said, that's great. We just wrote down a linear system of linear equations, and if we could optimize it, find the integer point that is the optimal, that minimizes the amount of wine you throw away, then we're done with the problem. Gurobi, a mixed integer programming solver that you can buy on the commercial market, or actually you're all academics, so you can use it for free, so you don't have to worry about that. It easily finds the optimal solution for 6 rats, and if we ask it to find the optimal solution for 10 rats, it turns out to be completely hopeless. So actually, we have a way to do a little bit better than completely hopeless. It turns out that we can make life a lot better by using symmetry. To add symmetry to the problem, we just say, okay, we're going to say the set of what we decide to do with rats is going to have some extra symmetry to it. So if we cyclically permute the bits or cyclically permute the members of the set S, then the variables are all going to be the same. Actually, if we add cyclic symmetry, then it turns out we can use Gurobi, mixed integer programming solving, to find the optimal answer with cyclic symmetry, and it gets down to 80, just like we managed to do before. Finding better symmetry groups is hard. I would love to be able to do it. It turns out that a lot of the solutions that we found for smaller sizes turn out to have a lot of symmetry to them. I don't have a good answer to why the best solutions we found so far turn out to be symmetric, but since they do, we decided to try looking for symmetric solutions. And so, for example, there's only 144 different size 16 subgroups of S10. And we could like take each one of those 144 of them and let Gurobi chew on the mixed integer programming with each of those symmetry constraints for like half a day and see what happens. And it only takes a few months worth of computing time. And if you happen to have a lot of computers sitting around, you can get away with doing that sort of thing. And at Google, we do have a lot of computers sitting around. So the best one that I found is this one particular subgroup of order 16 that manages to get down to throwing away only 18 223rds of the wine. It's a rational number as a solution, as the mixed integer programming answer often is, which means that I can throw away 77¼ bottles of wine approximately, or 78. I have no reason to think this is the best, though. All I know is that this is the best I can do right now. Mixed integer programming turns out to be a really useful thing. There are lots of sorts of problems that come up in the world, including problems that come up at Google, where mixed integer programming is the right way to solve them. The sorts of problems like, what is the best way to pack a bunch of computing jobs into a data center where I have a bunch of computers and each one has a limited amount of RAM and a limited amount of disk available to it and a limited amount of CPU and a limited amount of I/O bandwidth? Packing a bunch of jobs that have different requirements into data centers that have capacity sizes is exactly a mixed integer programming sort of problem. Or if you're Google Fiber and you want to like run fiber to all the houses in a city and you want to figure out which lampposts you want to actually put fiber relay boxes on and you want to minimize some cost to wire up all the houses and there are a bunch of extra things you have to do based on which lamppost you decide to use, that's the kind of thing where mixed integer programming and the set of techniques that we use for solving it turns out to be really helpful to a lot of cases. Mixed integer programming that we do at Google actually solves a bunch of those problems really well. It turned out to do a terrible job on the rats and wine bottles, so it's kind of lucky that this is not a very important problem, because if it were really important, we would do a crummy job of solving it. But on the other hand, you know, at least we got down to only throwing away 78 bottles of wine, so that's something. Thank you very much. Please.
Instead of being a pessimist, I was just a pragmatist, and I didn't care about minimizing the maximum amount of waste, but rather I just cared about minimizing the expected value of the waste. How would that change your methods?
Yeah, that's a good, so the question, if anybody's watching on the video, is what if you just want to minimize the expected value of the amount of wine that's being thrown away, as opposed to minimizing the wine that's being thrown away in the worst case? I don't actually know the answer to that. There are a variety of techniques that you would use for that also. It turns out they're almost entirely a different set of techniques than what you use to minimize things in the worst case scenario. And there are plenty of times when what you're asking is the right question to ask also. But actually, I have no idea. Sorry.
So there are a lot of really great recreational math problems out there. So how do you determine which ones you want to test?
Yeah, there are a lot of great recreational math problems out there. It's true. Which ones? I mean, I think that's a, which ones do you spend your time playing with? I think that's more of an aesthetic question than anything else, right? I mean, it's not a deep question. Well, I mean, it is a deep question, as all questions of aesthetics are, but it's very personal. I really like problems, well, personally, I like problems that are catchy enough that when you see them on a poster, it makes you show up to a talk about them. So anything involving wine for the adults or rats for the kids in the room seems like a good way to go. I like problems that are combinatorial in nature. I was a combinatorialist back when I was back when I was employed doing math. And I like problems that computers are good helping at, and where computers can give you insight that you might not be able to get in other ways. And also I like problems where like the fact that a solution exists is really surprising. As Jen mentioned earlier in the talk, I for a long time edited a column in the Mathematical Intelligencer in which many problems that appealed to me showed up. And so, you know, I can tell you examples of other problems that appeal to me, but I don't know a good way to characterize them in general. Do you know the wallets and lockers problem? Have you heard this one? Who knows the wallets and lockers problem here? Oh man, that's a great problem. I love that problem, right? So the way this problem works is you take 100 of you and 99 of your friends, like 100 friends, and you take away all their wallets and you put them in 100 lockers labeled 1 through 100. And then you have each of the 100 people go into the room one at a time, and your goal is to go into the room and find your own wallet. And you're only allowed to open 50 of the 100 lockers in order to do it. So it seems pretty obvious that you've got a 50-50 chance. Like no matter what algorithm you use to decide what lockers to open, you only have a 50-50 chance. But actually in this problem, all 100 people get to talk to each other beforehand, and then each one of them goes into the room one at a time, tries to find their own wallet, but has to leave the room exactly the way they found it for the next person to go in. And they don't get to give any information to the next person, right? It's like all 100 people are kind of doing it in parallel in 100 different copies of the room. And you know the first person's only going to have a 50-50 chance. There's nothing you can do about it. But the question is, how good a job can you do of making the chance that everybody finds their own wallet as high as possible, right? And it turns out the answer is a lot better than 1 out of 2 to the 100th. The answer is like you can do it more than a third of the time, right? So it's like shockingly good that there's this like amazing solution that you can come up with that totally blows you away. But at the same time, if you say, okay, there's actually 50 of you, and half of the lockers have a wallet in them, and half of the lockers are empty, and now what chance can you have of finding your own wallet, and what chance can everybody have of finding their own wallet? Nobody has any idea, right? And so there's like some big range of possible problems that are kind of versions of this same problem, and some of them we can solve, and some of them are completely hopeless, and we have absolutely no prayer of being able to solve, and we hope that somebody will come up with some good idea in the future that will tell us where the boundary between these two solutions is. That's another problem that appeals to me. And maybe if you squint at it funny, you can see some relations to these rats and wine bottles problem, where there are some things that we can know and some things that are completely unknowable to us right now. And I like kind of parameterized problems in that way. Please. What do I do at Google, and how does it connect with this? At Google, I work on making the internet faster. I've worked at Google for, yes, thank you, I appreciate it. This was a real difference when I stopped being a mathematician and started being, started working at Google, because at cocktail parties, you're a mathematician, and all of us mathematicians have developed this skill of answering the question, what do you do, to answer the question for non-mathematicians, right? And so you say something like, well, it has something to do with prime numbers, and well, when your computer talks to a website and there's that little lock icon in the corner, it has something to do with that, yeah, forget it, right? And now I work at Google, and I get to say, I make the internet faster, and people say, thank you, it's great, I love that feeling. So actually, my whole career I've spent trying to make things more efficient, trying to make things faster. And back when I was a mathematician, I tried to make math stuff faster. And when I was working on biology, I tried to make computations involving understanding DNA faster. And I tried to make speech recognition faster and things like that. So now I make the internet faster instead. In particular, what I work on at Google is making ads faster, because it turns out that ads do a lot of slowing down the web. And that's bad. We would rather the web with ads be just as fast as the web without ads. In fact, there are kind of a bunch of things that are downsides of putting ads onto web pages. I mean, there's upsides, like the fact that the web page can continue to exist because the person who writes the web page makes money, and they can pay for writing it and pay for the servers that send it. So there's a bunch of good reasons for web pages to have ads on them also. But unfortunately, there are downsides as well. So I work at Google in the group that tries to make it so that you can put ads on your web page without it hurting your web page in any way. So we don't want it to be slower, we don't want it to be less secure, we don't want it to be more annoying to read or have it jump around while you're looking at it, or a lot of other things. So there's a bunch of people at Google who work on the general concept of trying to make the web a better place, because we like the web. Oh, and it doesn't have anything to do with mixed integer programming at all, actually. Thank you very much.